Hello everyone and welcome back to Full On Entertainment. Today we are tackling a fresh calculus question from the JEE Main 2026 April 2nd examination that tests your core understanding of definite integrals and piecewise functions. Take a look at the problem right here. We have a definite integral to evaluate that goes from 0 to 3 and the integrand is e to the power x plus e to the power minus x divided by the factorial of the greatest integer function of x. Now when you first see this expression, the factorial of the greatest integer function in the denominator looks like a massive obstacle. Why is this term the key obstacle? Because the greatest integer function is not a smooth continuous curve. It is a step function. If you look at its graph as x moves from 0 to 3, between 0 and 1 the value flatlines at 0. At x is equal to 1 it instantly jumps to 1 and at x is equal to 2 it jumps again to 2 and so on. Because of these sudden jump discontinuities at integer boundaries, that is x is equal to 1, 2, 3 and so on, you cannot evaluate this integral in one continuous sweep from 0 to 3. Trying to find a single antiderivative for the whole range is a mistake. To solve this, we need to break our domain, that is from 0 to 3, into individual continuous intervals where the greatest integer function of x stays constant. Let us look at what happens to that denominator, that is the factorial of the greatest integer function, across our three integration zones between 0 and 3. The first interval is from 0 to 1, 0 closed and 1 open. So here the greatest integer function of x will be 0 as the numbers are from 0 to 1. So taking the factorial of the greatest integer function gives us 0 factorial, which is 1. For the second interval, that is from 1 closed to 2 open, here the greatest integer function of x is 1. So taking the factorial gives us 1 factorial, that is 1. The third interval is from 2 closed to 3 open. Here again the greatest integer function's value is 2. Taking the factorial gives us 2 factorial, that is 2. Now notice something important here. For both interval 1 and interval 2 spanning all the way from 0 to 2, the denominator simplifies to just 1. Both have the same value. It is only when we cross into the third interval, which is from 2 to 3, then the factor changes to 2. That simple breakdown completely demystifies the problem. Now that we can rewrite our original integral from 0 to 3 as a sum of three separate well-behaved integrals. So we can write I is equal to integration from 0 to 1 e to the power x plus e to the power minus x divided by 1 dx plus integration from 1 to 2 e to the power x plus e to the power minus x divided by 1 dx plus integration from 2 to 3 e to the power x plus e to the power minus x by 2 dx. Since the integrand in the first two parts, that is from 0 to 1 and from 1 to 2, is just identical, that is e to the power x plus e to the power minus x with a denominator of 1, so we can merge these two different integrals from 0 to 1 and 1 to 2 into one single integral from 0 to 2, and that becomes integration from 0 to 2 e to the power x plus e to the power minus x dx. For the third part from 2 to 3, we factor out the constant denominator 1 by 2 outside, so that becomes half of integration from 2 to 3 e to the power x plus e to the power minus x dx. So putting them together gives us integration of 0 to 2 e to the power x plus e to the power minus x dx plus half of integration from 2 to 3 e to the power x plus e to the power minus x dx. Just like that, the greatest integer function and the factorials are completely gone, and we can simply solve the integral by using the methods for exponential functions. Now we are left with standard calculus. Recall that the antiderivative of e to the power x plus e to the power minus x is simply e to the power x minus e to the power minus x. Let us evaluate both parts step by step. So first we integrate from 0 to 2. So we have integration from 0 to 2 e to the power x plus e to the power minus x dx is equal to, then we replace it with the antiderivative and it becomes e to the power x minus e to the power minus x evaluated from 0 to 2. Plugging in our upper limit 2, we get e square minus 1 by e square. And for lower limit 0, we have e to the power 0 minus e to the power of again 0. So e to the power 0 minus e to the power 0 is simply 1 minus 1, that is 0. So the whole term simplifies to e square minus 1 by e square. This is the first part. Now let us integrate the second term from 2 to 3. So we have a constant term 1 by 2 outside. So the expression is half multiplied by integral from 2 to 3 e to the power x plus e to the power minus x dx is equal to half of, then we replace it with the antiderivative, that is e to the power x minus e to the power minus x evaluated from 2 to 3. Plugging in the bounds for 3 and 2, we get a half of whole multiplied by e cube minus 1 by e cube minus e square plus 1 by e square. So this is after opening all the brackets. So this is our second term. Now let us bring both parts back together to find the final answer. So I is equal to e square minus 1 by e square plus half of e cube minus 1 by e cube minus e square plus 1 by e square. So combining the like terms for e square and 1 by e square, we get e square minus 1 by e square is equal to half e square, and minus 1 by e square plus half of 1 by e square is equal to minus half of 1 by e square. So factoring out the common 1 by 2 from all the terms gives our final expression, that is I is equal to half of e square plus e cube minus 1 by e square minus 1 by e cube. Checking the exam options, this gives us the correct option, that is option number 2. So whenever you see greatest integer functions or step functions inside a definite integral, don't panic. Identify the jump discontinuities, split the domain into unit steps, and solve each piece independently. If this visual breakdown helped you master floor functions, especially in calculus, smash that like button, drop a comment with any questions you have, and subscribe to Full On Entertainment for more step-by-step math solutions. Thank you for watching, and I will see you in the next video.